I'd like to welcome you to the Astronomy Update Lecture. My name's Gary Tomlinson, and I'm a GLPA member. And I've been asked to introduce our Astronomy Update Lecturer this afternoon. GLPA instituted this update lecture in 1988 as a way to update our members on astronomical concepts and information that has recently changed. A trivial example of this is like the number of moons Jupiter has. 12, right? That's what I learned. Yeah. The update lecture has consistently been the highest rated conference event at GLPA conferences. And I've had the honor to introduce our update lecturer ever since he first gave it in 2009. For those who don't know me, congratulations. Or my sense of humor, I should tell you that my introductions have been anything but traditional. I've known Ron for over 45 years. And for those 45 years, we have traded jabs at each other. This will be no different. Ron was the graduate assistant, and I was the undergraduate assistant at the Planetarium at Ball State University, where Ron now directs the newly constructed Charles W. Brown Planetarium. Oh, you gave it away already. It's over there. He was the best man at my wedding. Now, that was not his official title. That's just how my wife described him. I could tell you about all the books he's written. One book he co-authored, a textbook on photometry, which is now the industry standard. I could tell you about all his publications, all of his honors, all of his research. But I wanted to tell you things you would not find on his resume. Ron has had opportunities to go into a couple other professions. Ones that would have made him a lot more money. And notoriety. He'd been famous. But he really wanted to be an astronomer. And that's probably why most of us are in this profession, the love of the profession, not the money. And Ron wanted to be a professional astronomer. I seldom post on Domel, but a couple years ago I did, concerning PhDs astronomers running planetariums. I noted, talk about controversy, in general, that is not a good match. My observations have been, there are exceptions, that PhD astronomers do not make good planetariums. It takes a rare individual. And Dr. Kachuk is one of those rare individuals who's not only good at research, he's also good at teaching. He's good at all things planetarium. God, I hate that man. I know he's good because I've seen him in action. I sat on in his 1973 Astro 101 class, and I saw a very effective teacher. I learned concepts I should have known from his Astro 101 class. Used to be there were a few places one could learn about our profession. You know, the Spitz Institute, that's still around. Michigan State University, I'm a proud graduate of that program. The Strassenberg Internship, University of North Carolina at Chapel Hill, they're not around anymore to my knowledge. But Ron used to run a summer program in planetariums, and he's thinking about resurrecting that. He's changed his mind. So if you're interested in something like that, please see Ron so he has a gauge to go back to his administration and work on that project. Did you know that Ron used to write the astronomy updates for Encyclopedia Britannica? And you see what that accomplished. They don't print that encyclopedia anymore. But I can tell you, after years and years of painstaking research, Ron recently made his most outstanding discovery to date. The dome to the observatory does open up. Yeah. Ladies and gentlemen, you're in for a rare treat. The man who wanted to be and is a professional astronomer, Dr. Ronald H. Kachuk.
Thank you. I hope this mic's working out. It's an honor. Always is, except the first part here. It's always an honor to do this for GLIPA, but now for a whole lot of you is excellent. I want to start a little off the beaten path. Scientific method got mentioned a lot yesterday. We all teach it in one way or another, sometimes explicitly, sometimes implicitly. One of the things about the scientific method that tends to be undersold, underemphasized, is honesty. Honesty. You have to admit, even to the NSF, that you took $2 million to this experiment and it didn't work. Or you spent, and this is a true story in my case, we just spent 8 years on a long-term project and we came up with bupkis. But no one knew what we were going to find. That's research. So let me pose this honesty thing in kind of a realistic, down-to-earth way. What I need is a volunteer. Stand up, Gary. Thank you. No, stay right there. I don't want you too close. Now, this is the example. All of us, at one time or another, fly. Some of you may have flown into St. Louis. He used to fly. Well, the TSA, well, we won't get into TSA. This is some list or something. And suppose you're confronted with the following situation. Suppose Gary was hit this following situation. Sit down, Gary. We're overbooked. I'll give you the co-pilot seat if you know how to fly. Now, you really want to get there on time. So what's the answer? Well, common sense, of course. If you don't know how to fly, who knows how to fly a 747? So what would Gary do? He says, yeah. Now this is why this is a bad idea. Well, anyway. From time to time, I've been asked the following. I cannot possibly, in the time we have, even scratch the surface on all the things that have been done and published in astronomy in the last year. I go from October to October. In fact, I was adding things even 2 days ago. I try to make it as current as I can, but I heard something on the radio today. I don't know if that qualifies. How do I pick? How do I choose? Well, it better be interesting, obviously. I'm doing it for you folks. I like surprising results. That's the fun part of doing science, surprises. Cool ideas, that's always great. I like to recognize, I'm going to point one of these out in a few minutes, important or likely to become important new discoveries. We've got a couple of those cooking right now. Something particularly of interest to people who are planetarians, certainly, and interest to your audiences or classes or whatever you're teaching. So, this is what happened this year. Throughout the year, I collect and skim articles. Most of them are electronic format. I'm doing it, initially I'm doing it as a rejection. Most I don't, I look at it and say, no, that's not interesting, that's not what we want. But I keep throwing things in bins on my computer desktop. I will start that probably tomorrow for next year. No joke. Early in the fall, I reduced the list further. This year it was down to 44 topics based on 198 articles. Yes, I looked at 198 articles. Did I read them all carefully? No. Some I had to. In some cases, the articles were not elementary, they were actually in the Astrophysical Journal. So it was technical. I do that when I read something in the popular press and I can't make sense out of what they're trying to tell us. And then I'll go back. I have sometimes found humongous errors in what they were telling us, including one case, a certain magazine will go unnamed, but space.com was quoting this research about an exoplanet, and if you read the description, you got the idea that somehow in the atmosphere of this planet there were shards of broken window glass blowing around at high-speed winds. I said, I got to check that out. They listed the source. I went to the source they listed. It was the wrong article. It was to an exoplanet, but the completely wrong one. Finally tracked down what they were looking at. Yeah, the research said maybe, kind of, possibly, there might be little tiny bits of glass in the atmosphere. By tiny bits, micron size. But that doesn't sound cool in an article. I get to a final cut tonight. We got 18 to go. 18 left. Although I think I may have gone up or down one since I wrote this slide. But I'm going through all this stuff and presenting it, and that brought to mind an interesting quote I ran across recently. I'm about to present my research. If you don't see something you thought was really cool in the news, sorry, this is what made the cut. And it's just the way it is. I can't do it all. We'll start with Jupiter and Saturn, and obviously you can't go very far without talking about Juno. Start close to home. You know, the craft wound up in a 53-day orbit. This particular orbit, I'm about to take this mic in hand because I got to turn this. For the earthquake, I need to point to this thing better, so I need to turn. Anyway, if you look over the screen, Jupiter's got these radiation belts around it. It's shaped like a donut, a torus. All our spacecraft to date have stayed outside of that because that radiation levels in that torus are exceptionally high, and you're going to fry your electronics trying to go through that. Well, Juno's got a polar orbit, so it comes inside. It's still pretty high radiation, but nevertheless, this is a much better deal. And getting very close to the planet, that's the key. That has never happened before. We've never gotten that close. And so we've had a lot of preliminary results. Oh, by the way, the orbit's 53.5 days. That was the original insertion orbit. And the plan always was to change that to a 14-day orbit. There was a fault indication on one of the fuel valves on the rocket. So there was a slight possibility that they fired the rocket again to change the orbit to a 14-day orbit. They might not be able to turn off the engine. Thinking that might not be good, decided not to risk it staying in the 53-day orbit. NASA extended the mission for that reason, because it's obviously going to take longer to go around. It's now done 7 passes of Jupiter. And see how close it's getting to the clouds here. Now, by doing that, what we're learning is phenomenally different than what we expected. This should run in a second here. Let's see if it goes. This has been put together by a bunch of stills. It wants me to click it. I'm always amazed how things always work at home. Here we go. This has been actually put together a bunch of stills from the camera. You're looking down at the North Pole. It's coming down from above. And we're going to swing around and go right through the equator. Maybe you've all seen this already. This is really well done. Now, the North Pole looks a lot different than the rest of Jupiter. Now, the contrast in colors are height a bit. They have to be. Here we go. Past the equator. There's the equator. Southern hemisphere, broken glass, right? Shards. There's the South Pole. Notice that looks nothing like the thing you saw in your telescope? The polar regions are a complete surprise. Sometimes I have students that think we get upset when we don't see what we want. No, we celebrate. Heck, that's grant money. Let's go forward here. That's just a still now. So I can look at this polar region a little more carefully. It was thought before Juno got there. Remember, we've had all kinds of, we had Galileo orbiting this planet, remember? So we thought we knew a lot about it. Well, I pulled out my lecture notes. I'm teaching astrophysics this semester. I hadn't taught it in a couple of years, only a couple of years. And I pulled out the notes on the solar system. I got to Jupiter. I said, well, tomorrow I got to do this for the class. I opened it up and I looked at it and said, this is all wrong. I'm not exaggerating. It was all wrong. We already know better, just from going in closer. It was thought that you see clouds in these pictures. You get beneath the clouds, it would be a nice even mix and of different elements, compounds, molecules, and it'd be more or less even, nothing too complicated. It turns out the complex features you see here, it go deep into Jupiter. That was a big surprise. The polar regions look chaotic. They got those cyclones in them. It's not quite sure why the color is so different. We have no band structure near the poles. It looks nothing like Saturn's poles. There's no hexagon, right? I guess the aliens didn't get there to make the hexagon. Now, this is a composite. We got the Hubble picture of Jupiter, but up on the north region there, oh, you see that? No, I got to use this pointer. The mouse pointer doesn't work for you guys with this mode I'm in. Up here, of course, this is all from ultraviolet. But look at this little thing. It looks like a tadpole or a comet. That's persistent as the planet turns. The magnetic field goes with it. This tracks with the moon Io. As Io goes, so goes that little comet. There's a magnetic flux tube from Io. We've known this for a long time. And it goes, and that's where it lands. Okay, that was cool. Now we're going to get into strange. This is an infrared image of the aurora. And you see all kinds of structure and all this. But what else? And these are some kind of defects, the white dots. Don't pay attention to those. On Earth, the auroras are produced by charged particles from solar wind, like a coronal mass ejection or something. Coming in, the particles get directed by the magnetic field. They come into the Earth's poles. They get down the lower atmosphere. They come with a lot of kinetic energy. They excite the atmosphere to make it glow. We need the sun. If the sun turned off, of course, it would ruin a lot of things, but if the sun turned off, we wouldn't have any aurora. That's not true for Jupiter. Here's the flux tube. I'm getting ahead of myself. There's Io. We've known about that tube for a long time. Basically, it's claimed that the radiation levels on Io in places are like being inside a nuclear reactor. It's really very intense. I'll come back to the other topic here in a second. This is the map of the magnetic field. We're already mapping that on these passes. This will get better and sharper. Right now it's kind of a blurry image. But we got, well, you can see we're going from plus 20 Gauss to negative 20 Gauss, north-south pole, north-south pole business. So we got pole here and pole here. But look at this, and look at this, and look at this. It varies a lot. Oh, by the way, that's twice as the strength we were expecting. See, now we can map that in detail. From a distance, this looks like a simple dipole. You get in closer, it's not so simple. And it suggests that the magnetic field is not generated in the core. It must be up much closer to the bottoms of those clouds. It's nowhere near the core. Now, they're mapping the interior using the fact that Jupiter has internal energy source, it's warm, and being a black body, thermal radiator, that means it also radiates microwaves. Twice in the media, I've seen how they said The spacecraft is beaming microwaves down to the planet. No way. How much energy do you think we're packing there? Jupiter is the source. And so they look what's coming in from the interior, and this allows them to translate. You take particular frequencies of microwaves, they're attuned to molecular transitions, so you can map things like ammonia. There's an ammonia pool at the equator. See that we've blown up this little strip here out to here. This isn't evenly mixed at all. There's a weather cycle of ammonia. No, I don't understand that. Okay, big debate before we went. What really is inside? This is where my notes really went, my class really went south in a hurry. They said, and I've taught it for years, there's a core inside there of rock. And it's about the size of the Earth, maybe a little bit bigger. We thought that in part because, well, we didn't know any better, but our models for how the planet formed made sense that there would be a rocky core, which initially had enough gravity to track things in the solar nebula and collect the ices. Ices gave it more mass. You get enough mass, then you can hang on to the thin gases. Well, what if there's no core? We had two models, core and no core. Which is right? Neither. How can that be? First of all, how would you even know? Well, it turns out we're so close to the cloud tops here. The blue line is the average trajectory that the spacecraft should have been flying. Now, you all, at some point, if you teach upper-level courses or even introductory astronomy or took such a course, they told you how all the gravity of a planet acts like it's all in the center, like a point mass. Hogwash. Only if you're far away. As soon as you get in close, all the knots and bumps and warts, they all have their own gravity. And so, unless you have an interior that's perfectly uniform, as this spacecraft flies over things that are denser, it gets pulled in. By mapping and measuring the Doppler signal from this thing on the Earth, we can tell you how it's wiggling. And that allows us to map what's inside. And that's how we thought we get the signature. There was a nice rocky core. The people who are looking at the data are stumbling for words to explain what this is telling them now. It looks like it may have a core, they're calling it fuzzy, and that it doesn't seem to have a sharp edge. And it's not a little thing in the middle, it's half the planet. No, this isn't what we thought. Isn't what we thought at all. Now, let me check, because I think I missed a topic here. Let's see what the next one is. Well, let me back up just for a second, because this is really way back. That picture. I saw that and made me start to think about it. Remember I said about auroras and how they're made from the Earth? And we need the sun, which sends charged particles in, and they get pulled on magnetic field lines. Jupiter does its auroras all on its own. The charged particles are going the other way. They're coming out of the planet. No, we don't know how it's doing that. So you could turn the sun off, it still has auroras. It's just the shocking thing. Literally, at the poles of the planet, charged particles are streaming out, hitting the magnetic field lines and swirling around. That excites the gas, and it glows. But it's going out, not in. This is weird. You remember this one. That's probably the closest, it is the closest picture we've ever gotten. It passed, the probe was 5,600 miles over this when it took that picture. Yes, colors are exaggerated. Contrast is hyped. That's not always a bad thing. You just see more detail. We call it a hurricane. That's a pretty bad term because it's not. In fact, it's not like, hey, it's a storm. It certainly turns. There's no eye or eye wall in here. Wind speeds are high. We all know that. But I don't know if you're aware of the fact that it's disappearing. Yeah, it is shrinking, obviously. I mean, it's even obvious to my eye when I look at the telescope these days from what it was when I was a kid. We don't know why. Of course, we don't know why it was stable in the first place. So now we're all worried because it's doing what we thought it should. Don't worry. And the color's changing. And Jupiter has rings. Remember that? Jupiter has rings? Remember these dusty rings? You've seen some pictures of it, but not this picture. This is from the planet looking out. Whoops. Yeah, that's it. I got it. Yeah. And they're kind of dusty. And you can't see them real well, but by the way, Planetarium people, this is a constellation shootout. We have 3 stars in a row here, a bright one up here, another one here, and kind of a little, what does that remind you of? Constellations don't change anywhere in the solar system. Orion, yes. No one will be eliminated here. All right, I want to go through this kind of quickly because you all know about this. There's no way I can take 13 years of orbital discoveries and do anything and do it in 5 minutes or less like I have to do. So I just put in some pretty pictures. It always works. It works for audience. It's still educational, gang. I never apologize for just showing pretty pictures because I always wind up telling them something. That's the Hubble picture, by the way. That's not from Cassini. But it puts things in perspective. Then we got this stupid thing we can't figure out. That's the North Pole. There's none at the South Pole. And there's none at Jupiter. And there's been some attempts to reproduce this in labs, obviously on Earth. I'm not sure I'm convinced of that. I don't know if you know this or not, but this is shrunken. And if you were flying here, this is actually elevated like a few miles. Yeah, it's one of those things you change the slide quickly. Outer F ring. We knew about that, but never in this kind of detail. This is that detached ring. By the way, anytime you see a nice narrow ring, it screams one thing only: shepherd moons. All right, what's going on here? That happened during the mission. So there's some sort of collision or something. In other words, even on short time scales of days or weeks or months, things change. Despite the fact it always looks the same in your telescope. Cassini division. I always point this out. You know, when I was in college, there was a discussion from NASA about someday we're going to send a spacecraft through this because it was all empty. I'm not sure what tipped them off that was a bad idea, but obviously there's lots of stuff in here, and we can see ring structure like crazy. But I have to point out to people that from here to here is the width of the United States. Put things in perspective. You can always give that to audiences in miles, but you tell them the size of the United States, that means something. All right? No, we're all that way. Now, one of the highest resolutions of the rings ever taken, this is in the B ring. And you see color differences, and we're not quite sure what all that's about. And all these breaks and things are resonance and orbits. You know, you take astronomy and you learn about essentially two-body problem. That's what Newton's law of gravity is. You got, object M1 and M2, and you got this distance between them, and you figure out the force of gravity. You give it a homework problem over, G, M1, M2 over distance squared. I hope you know that really doesn't work anywhere, really. Because we never have just two gravitating bodies. We have what we call the n-body problem, which is another way of saying a pain in the butt problem. You have to do a numerical simulation. You just can't do it any other way. And even if you do the simulation, you're never sure you ran it in the computer long enough, because you let these things long enough, all kinds of funny things will suddenly happen. We're not convinced the solar system is stable. No, and that's not a joke. Yeah. Given enough time, enough gravitational interactions, who knows? You can't, there's a little bit of chaos theory in this, all that kind of good stuff. Anyway, this is really an in-body problem. Even these little ring particles that this might be a few hundred feet across, they have gravity. And they do funny things in the rings. Look at that little thing. It's cleared this out. Yeah, Keeler gap. And these little ripples here at the edge, casting shadows, those are a mile high. So ring particles are reacting to the gravity of this little asteroid-sized object, and they're kind of creating these waves features in the rings. Oh, they can get worse. Here's the edge of the B ring going out from the planet out this way. You see the shadows being cast by this. This was shocking. These are places 2 miles high. Now think about that. The rings are incredibly flat. You can go for thousands of miles in your little space copter and set it to just hover, 10 feet or so above the rings, and you can go for thousands of miles and never worry about hitting anything. Then all of a sudden, boom, there's a wall 2 miles high. Yeah. Titan. Well, you could talk about this one for a long time. What I like about this, yeah, near infrared, I thought so. This is glinting of sunlight off lakes of methane, liquid methane. Watch. Clouds. Methane clouds. Where do clouds mostly form on the Earth? What latitude? And we know what latitude we're looking at here? It's not the equator. It's the pole. No, we don't get that either. But then again, this is a very different kind of, by the way, of course, you might remember that this is the only moon with a really significant atmosphere. It's 2.5 times, it's about 2.5 times or so roughly what you're breathing now. Then we have Enceladus, remarkably reflective. It's all ice. It should have been very boring. It should have been full of impact craters. It's only 300 miles across, so it should be ice cold literally in the center, and therefore there should be no volcanic activity of any kind, and it should be dead and boring and stupid. Instead, it's got water geysers. It is warm inside. There is liquid water, although it's not pure water, but there's liquid water in the center, and it's all due to tidal heating. Now, you know where it might be the best place in the whole solar system, other than the Earth, of course, to look for life? Here, not Mars. You've all seen this one, I know. And if you're like me, you love to point out to people, well, first of all, you're seeing the sun eclipsed. This is all forward scattering. The night side in here, which isn't dark, is lit up by light from the sun reflecting off the rings. But the thing I'd like to point out, and I'm sure a lot of you do too, is that little dot right there? That's Earth. It always gets a reaction, whether it's from college students or from whoever. Never miss an opportunity to humble the audience. And I mean that sincerely. It's important. It's part of that inspirational thing. I always point that out. Okay, enough from Saturn. I don't want to, you all live this. I'm not going to go through this with you. Yeah, I'm a little sick of it myself. So we're going to go through this really quickly. I'll show you my picture from Muncie, where we were 90%. And as soon as the eclipse started, we have almost a citywide power failure. For some strange reason. And it was the first day of class at the university, so we had 20,000 students on campus. And power goes out in the buildings. Oh, go outside. And look at the sun. This is taken by a fellow planetarium, Keith Turner. I want to show one taken by a planetarium person I knew. And of course, you all saw this stuff until you were sick of it. We distributed 5,000 viewers. The university distributed another 10,000 viewers. The university ran out of eclipse viewers at 9:30 in the morning. Now, there's a dark side or a backstory to the eclipse viewing that you probably have never told an audience. So you're not told students, kids, little kids. It's the real story of the three blind mice. Three Blind Mice, the early days. Okay. I couldn't resist that one. On to stars. Show you some. Oh, you've seen pictures like this before. This is the Scorpion, of course. Right? And you have Antares looking nice and red. And you have the dust lanes here. Sagittarius is just off the slide. Let's look at this, blow this up right here. Unfortunately, it's going to get turned. But just this area right in here. I don't know if you know, it's the prettiest area of the sky. And Antares is now here. All this is dust scattering light from Antares. Some of that dust has been created by, this is a red supergiant. Some of this has been blown off by itself. This is like 620 light years. Here's a globular cluster in the background. I forget the M number on that one. But that's another 6,000 miles. Is it, what, 74 or something? Oh, that's M4? Why do I want to go 70? I'm thinking of galaxy. I know why. Star has got something like 15 solar masses, 10,000 times the luminosity. It's almost 1,000 times bigger. But I hope you know, in fact, I know you do, the stars aren't resolved in telescopes. I have to tell students over and over again, even graduate students, that because this one is wider than that one, I might go higher so you can see it, because this one looks wider than that one doesn't mean that that's bigger. It just means it's brighter. Stars are unresolved. They all have the same width on a good set of optics. If you really look at the profile width, it's the same. I had to force a grad student to do that one time. Plot it, we have the software, click on the image. Well, there are tricks though. There are about a half dozen stars we have seen the surface. They're big supergiants like Antares and relatively nearby. Well, here's a new image. That's Antares. We have this for Betelgeuse as well. I've had that for years. And the trouble is, that doesn't look like the textbook. We model this in my astrophysics class. Of course, what we have is a uniform, nice spherical thing, and all that kind of stuff, and the density's nice and, composition's uniform. And the computer comes out with this nice model, which is science fiction. We have bright and dark areas. No, we don't know what this is. There's enough Doppler data, though, we can tell that some of this stuff is rising and falling with speeds that are, if you like the English system, 45,000 miles per hour. There's stuff that extends out a full diameter from the star. No one is sure what's driving this. Convection, our models of convection do not account for this. People are talking about new physics, literally, new physical process. Okay. How about ones that just go away? We've wondered for a long time, if you have a big star and the nuclear fuel in the center runs out and it collapses under its own weight, we always say, oh, that goes to a supernova. Will it always? What if you've got a lot of mass? Is it possible the whole thing just goes right down to a black hole? There's some simulations that said that's what would happen, could happen. So what means you'd have a picture where the star would be there one night, not again. This is a star estimated to have been about 25 solar masses. It's in a galaxy, notes, NGC 6946, I don't remember that, but 22 million light years away. The star did have a history. There was some recording in archives of this thing. It had been constant brightness for about 10 years prior to this event. In 2009, it suddenly got brighter a million times the luminosity of the sun, actually. That's still not a supernova, by the way. Supernova is much more higher than that. And of course, no one watches these things every night. When they came back, all they know is a few months later, when this picture, this is the one on the right, was taken, it was gone. Now, you might notice the one on the right, there's all kinds of stars in here or something. Yeah, but we can centroid that very accurately. We can tell you it lines up with nothing over here. Is it really gone, or is it just a really weird variable star? We have to keep watching. If it comes back, of course, so much for that idea. Although we've got another mystery, like what is it doing? Merging. It can happen. We think we've seen it. You recognize this place, but maybe not that spot over there. That's the location of a star that was in the the Kepler survey. If you like numbers, it's KIC 9832227. Isn't that romantic? That star is expected to explode in 2022, give or take a year. It could go to second magnitude. I've never in my career had anybody predict an explosion. Talk about putting your career on the line. Well, this is what we currently think it looks like. This is a model, computer model based on the light curve. This is a contact binary. I don't know if you're familiar with this, but realize this, but this kind of thing where stars are literally touching is exceptionally common. Among binary stars, this kind of contact binary is very common. I've studied many of them. I've had students work do projects on these things. Currently, this thing has an orbital period of 11 hours. They're that close together. But the period is growing shorter, which means they're getting closer. And it's accelerating. That put together is a red flag that we're going to see a merger. We think we've seen this before. Oh, I should show you the data first. Don't worry about all the funny units here. We got time. You see the years across the top on this one over here on the left. This is the orbital period, and it's just going down. Orbital periods of binary stars do change, but not like this. Over here's the light curve, and this comes from different surveys. They have various levels of precision. Some are good, but they're all automated. But the light curve is changing. Up in here, they go up and down, up and down. They get bright when you see the two stars broadside, but when they turn toward us, you see them more or less in on. You have less surface area, so it looks dimmer. Up and down, up and down. But look at the bottom one. This is the last one. These heights don't match so well anymore. Well, anyway, I cheated though. What you're seeing isn't that same star. This is the one that did blow up the same way. This is V, 1309 Scorpio. It's a contact binary. It blew off, and it went on as a red nova. Nova are always blue. This was red. Here's another one. That's a Hubble image. We think it's the same thing that happened. All I know, this is V838 Montosaurus. I was on a telescope in Arizona, and I got a phone call in the control room. Please, baby Corns, go over this. This thing's gone off. We don't know what it is. Get us any data you can. So I went over, and all I had was this really bright sucker. I think it was 6 magnitude. It was too bright for a telescope to do much with it. And then later I said, oh, well, okay. I gave him a couple of data points, and then this beautiful Hubble image came out a few months later. Then there's the weird stuff. Very weird. You've probably heard of Tabby Star. I talked about it last year. You're going to see a couple of the same slides from last year. It's another thing this Kepler, discovered. We got 2 images here. This, what do I got here? Yeah, infrared and ultraviolet to show you that there's nothing particularly impressive about it. Yet it's doing funny things. It should be a perfectly normal star, and it's doing things normal stars don't do. It just suddenly drops in brightness. See it here. These are enlargements of some of those things. At first, it looks like, well, it could be a transit of a planet. Not when it drops 20%. So this has gotten a lot of attention. Skipping a few things here so we get back on time. We've seen about 10 dimmings. A lot of these are only 1% loss. Like I said, sometimes they're 20. They'll last a few days. And this got reported, oh, God bless the media, as an alien megastructure built around the star. Now, let me tell you why we now know, of course, common sense, but even beyond that, well, we now know that's not true. And this is the new part for this year. Those dimmings of the small ones that go down just 1% or 2%. They're wavelength dependent. Didn't know that before. That says it's dust. So there's some kind of clumps of dust that at least the minor dimmings are being caused by. If you put a solid structure, like girders from an alien structure, they don't do that. It goes black, it goes dark. I mean, that's it. Then there's this wild model. Try to explain things. Star up here is over here. See that pointer? And then there's a planet that happens to have a big ring around it. We need the ring. We need something nice and fat to get those deep dips of 20%. But it's got, at its Lagrange points, a whole slew of Trojan asteroids. They cause the minor ones. And if this model is right, you can expect some more dimmings in 2021. I'm not holding my breath for that. There's been long-term variations we don't really understand either. It had been reported that it was only dimming. We now know it can do both. And you can see some of the slopes in here. We got some of the Kepler data. Yeah, they've got big error bars because of the nature of the telescope and the survey. But it's good enough to see there's some variation there. This is supposed to be a run-of-the-mill star like the sun. You like mysteries? When I was in college, we heard about things called quasi-stellar radio sources. Radio telescopes are picking up things, signals, static, and once they finally figured out where exactly the sky was coming from, it turned out they were coming from what looked like stars. But I remember that all evolving. Of course, today we know those are supermassive black holes in old galaxies. I mean, talk about a huge discovery. It evolved slowly. I think we're seeing that same kind of thing beginning now with fast radio bursters. These were first noted in 2007, and the guy whose name I can't recall at the moment, who tried to publish, he found this in the archive of the radio observatories, got stone cold silence. Because what he picked up was a burst of radio energies, and it went away. The bursts are typically like 500 million solar mass, luminosity of 500 million suns for just a matter of milliseconds. So you can't really get a chance to get a telescope precisely on it. The radio guys can't tell the people at the Keck where to point their telescope, so it couldn't be followed up. We now realize that these go on all the time. They're not rare. There's a few a day, all over the sky. What's producing them? One is different. All the others are one-shot events we've seen. One time and gone. There's one that repeats. It's not periodic, but it does repeat. Therefore, you can use the VLA, you see this picture, to track down the position with great precision. We not only can tell you now it's from that galaxy. Not only that, we can tell you what part of that galaxy, that little fuzzy thing, we're talking about what part it is of that, can you believe it? It seems to be coming from a place of active star formation. Whatever this is, it's got something to do with youth and stars. It's got to do with something that's small, because 500 milliseconds, that sets the size limit. The thing is 500 light seconds across. So they think, oh, it's neutron stars. Neutron stars don't do that. They're thinking of pulsars. There's nothing periodic in any of this. Stay tuned. This is developing almost weekly. Exoplanets. Gotta watch my time here so you don't kill me. Exoplanets. Boy, these things are weird. We used to think, and I used to teach in class, that when the day comes, whoops, I goofed up, back up, I moved the mouse, I should never do that. That when we got to the point where we start finding planetary systems and other stars, they're going to be a lot like the solar system. Because of this vast sample we had of one. It was going to be just like that. We couldn't imagine it not being like that for all the good reasons. We got rocky planets in close and big planets outside, and they all go around the same direction. Oh my goodness, it's hard to find anything that looks as dumb as our solar system, actually. This one's black as asphalt. Of course, we need an artist's conception to prove it. WASP 12b. WASP is a name for a survey, and the star doesn't have any other name, so they call it WASP 12. It was the 12th one found in their survey. Lowercase b for the planet. It's a hot Jupiter. It's about 1.4 times the mass of Jupiter, about 3 times bigger, which is kind of funny. It orbits just under a day. That sucker's close. And it's hot. Duh. Yeah, I put the Fahrenheit in here. 4,700 degrees Fahrenheit is calculated temperature. It's going to be tidally locked. That means you get that close, and this is physics, you can't beat this. It's going to lock. It's going to be like the moon. One side always faces the Earth. One side of this is always going to face its sun. That means one side is always daylight, one side is always night, which means in the atmosphere, and it must have one, because it's got to be a giant planet like Jupiter, the atmosphere is going to have a huge temperature gradient across it, like 1,000-degree change day to night. You think it's bad here. That means, and the conditions are right. Oh, by the way, we've actually sampled the atmosphere with the spectrum. We have a little bit of the spectrum, and water vapor was detected. So there probably are clouds forming on the night side of water vapor. I won't bet on that, but you think so. Now, most of exoplanets, almost all of them, have been found indirectly by how they tug on their star or how they dim the star as they go around, the transit method or the wobble method or what you want to call it. There are only a few we've actually seen them. The trouble with seeing them is, of course, you got the star is so amazingly bright, you got to dim it like crazy, and then be patient, because if you can see the planet, it means it must be far from the star, which means it's got a long orbital period. Well, see what you think of this. I may have to click this a few times. Let me just not start it just yet. I want to point to something, hoping, of course, it starts. You've got all this funny stuff in the middle, which is just due to the process of dimming out the star. So is this black patterns. But I want you to watch this, and even that. Now, when this was published, I remember this came out, it was one still image. And they said, see, we found planets, maybe. And the response was, yeah, you also maybe have background stars. I mean, it's true. How do you know? Patience. Patience, yes. And what you find, they orbit. Let's do that again. Boy, easily impressed. I made that in Photoshop. No, that's real. In particular, watch the one out here moving even. Yeah. It has an estimated orbital period of 400 years. And even the inner ones are like 40 years. So obviously we don't have complete loops. That's enough though, it's convincing. Yeah, they're there. And then there's this mess. Discovered not by Kepler or Hubble, but by ground-based survey. This is TRAPPIST-1. It's transit, and we have monitored with our observatories at Ball State many planet transits now, and done projects on them. And so I know what these look like, because we've done so many of them, but not like this one. So here you got light brightness. One is 100%, and this is down 90.9, 3% drop down here. Here's time in minutes. And sure enough, bingo, it goes down because we got a planet coming across. And bingo, it went down again. And it starts to recover, and it doesn't recover too well. And then it comes up here and it kind of goes down again. Like, What's going on? Well, look down here. Here's the explanation. I don't know if you can see my red dot. There's the star, and we got some small little planets moving across it. There's 7. And they're Earth size. 7. Yeah, they're a solar system. Oh, by the way, the star is an M8 star. It's a dwarf star. It's only 1/10 of a solar mass, which means if you want to stay nice and warm, you've got to get close to that star. Well, it must be true. We got a picture. Of course, that's all artist conception. We don't know what they look like, but we do know something about their sizes. Now, media got all excited about this. Oh, there's got to be life. Some of those, it turns out like 3 of them seem to be in habitable zone. So that got a lot of excitement. Earth-sized planet in a habitable zone. Hey, that's for us. The first time I heard that reported, I knew that was probably bogus. You can't be that close to an M8 star. They're unstable. They flare. They have a lot of solar winds. They have a lot of radiation. So these planets have an atmosphere. It wouldn't take long for it to be blown off. It's unlikely these are nice places. Well, we didn't give up. Tau Ceti has got 4 Earth-sized planets. And if you look carefully, this is the solar system down below, but up here, not the scale, of course, they're not that close. But you see that this is the habitable zone in green. We got one just on the inner edge and one just at the outer edge. Should we get excited? Well, there's always putting a kibosh on this stuff, but this one, it turns out, its location plotted with the habitable zone here is, as the author of the paper puts it, with a lot of generous assumptions. That's his words. This one, while it might just be at the edge of the habitable zones with time around a star are not constant. As a star ages, its temperature and luminosity changes. The sun has gotten brighter over its lifetime. And so it may be this inner edge originally was in closer or even further out, but we're not sure that it was in a habitable zone very long. And you need length of time for life, which is really what we're looking for, of course. Then we got one that looks like it's made of packing material. This is a little hard to believe. But of course, we've got this picture, so it must be true. This is Kelt 11b. It orbits a subgiant star now. Orbit period is 5 days. It's about twice the size of, twice the size that we can explain. It's really large. There are models for the structures of these. They're good models, but this is not working here. It's about 1.37 times the mass of Jupiter, but it's only 19% of the mass. So it's bigger, but smaller in mass. Work out the math. Yeah, it's like 0.05 grams per cubic centimeter. Styrofoam. Yeah, anyway. Then there's the galaxies that shouldn't be. I've actually introduced this once before over the years. These are called ultra-diffuse galaxies. There's a galaxy here, in case you didn't notice, right here. Well, they have only about 1/1000th the stars they should, yet they're the same size as the Milky Way. And so they have such few stars, they're hard to pick up. The problem is, how did they form in the first place? One idea, they started off at really tiny galaxies, or galaxies form, which is still being discussed. But over time, gravitational tugs and pulls of neighboring galaxies stretched them out, made the orbits of those planets go wider, and so it got to be about the same size as the sun, but just started off as a runt. Or just that's the way they form. Let me show you some more. There's now then notice that there's one thing different about these guys, and you can see it in this picture, and this one too. See those look like stars? No, those are globular star clusters. They have too many. For that kind of mass, they shouldn't have that many globular clusters. Globular clusters, we think, form the same process that the disk and halo of a galaxy forms that requires a lot of mass, yet we don't see that mass. So we're on to something here. Exactly what it's telling us isn't so sure, but maybe when these form, there's enough time for the halo to form and some of the stars in the disk, and then for some reason star formation got cut off. No idea why. Then this guy's got too many black holes. That can be a problem if you live in the neighborhood. This is the galaxy, radio galaxy Cygnus X1. This is a radio image. Radio galaxy has two of these radio lobes out here. You see the jets of material coming out. That white dot is the entire galaxy. And it's a giant galaxy at that. It's elliptical. Yeah, so all this came from there. In fact, it came from a tiny part of it. It came from a massive black hole in the middle. Okay, what I want to do in the next picture is zoom way in. We're going to go into the core of this thing with a new image. And actually, it's two images. There's the core. Probably the black hole lives here. There's one of those jets going out. There's the other one. You notice this thing here popping in and out? That can only be one of two things. A supernova or another supermassive black hole that just, ate a star or something and got bright. Turns out that the pattern of brightness and the duration of this does not match a supernova. So Cygnus X1 apparently has always had two massive, supermassive black holes, but this one went unnoticed until it had dinner. That's about 1,500 light years separation between those two. Probably got that other black hole when it merged with another galaxy. Galaxy mergers will, well, even Andromeda has more than one black hole. I don't know if you didn't know that. It's got two in its core. Okay, dark matter. There's a twist here. I don't know if you knew this, but Vera Rubin passed away this year. She was the one that, essentially as a graduate student, woke our eyes up to the existence of dark matter. Now, it had been claimed before in various ways, but she made the case, her and Kent Ford. This is her. I like this picture because I use this telescope for years. I know the telescope exactly. I know about every bolt is on the back end of that sucker. So seeing her there, oh, gee, we have something in common. Except I think she got a better spectrograph than I did. A lot more help, too. I didn't have anybody. That's a 72-inch telescope out of Flagstaff at Lowell Observatory. Now, what they found in 1970, as her and Kent Ford, was that when you look at galaxies, you don't get what you expect. This is distance out from the center of the galaxy, and we superimposed the pictures. You can see it, and it's speeds of the stars going around. And what we calculate is, well, in the middle, the galaxy turns like a hockey puck, like a solid body. You get out here, though, the things go down like planets do in the solar system. The speeds go down a la Kepler's law. They don't do that at all. They stay almost flat. And she found that was true not just of one galaxy, but 70 some in original study. She's the one that taught us dark matter. So, here's this another way. In the nearby universe, within a few 100 million light years or so, all the galaxies, spiral galaxies do this, just what she found. They've got a nice flat curve. This is distance from the center. I know you can't read that. And that's speed. That is only accounted for if you have a big halo of dark matter around here. It's gravity that's making that happen. But there's been a new study. And this one, they looked at several hundred galaxies, but they were at a much further distance. Distance about 2.5 billion to 8 billion light years. Excuse me, I said that wrong. 2.5 billion to 8 billion years after the Big Bang. So we're looking at ancient history here. They don't do that. They do that.
Now we've got an interesting problem. Did dark matter not exist back then? No one buys that. In fact, it's kind of essential to our models of how the universe formed. It's necessary to have dark matter there. So the thinking is it's telling us more something about how galaxies formed back then or something. They didn't have the dark matter corralled or something. They wave their hands like I'm doing it. They have no idea. No, this is brand new, and this is kind of surprising. Kind of surprising. Okay. I'm going to end with Einstein's universe. You've heard a lot about this. Well, we've now had the third and fourth, but the third detection of a black hole merger with the LIGO gravity interferometer. And these have got masses one is between 25 and 40 million masses of the sun. The other one's between 13 and 25, and they merged. By the way, when you model this stuff, this is stuff from the LIGO detectors, you can model those wiggles, and you can get an idea how much power was radiated. And that gives you a distance, at least roughly. So you hear these distances on billions of light years. That's how they get to it. They have no other way of knowing. They often can't tell you where it is. But you see the different structures here. These are 4 detectors. By the way, this one don't look at because they're not confident of this one, although it looks good to me. But this is kind of the fits you're seeing. Notice how it appears and wiggle, 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 and poof, gone. What's happening, if you look very carefully, you may notice that the frequency is increasing. See how the wiggles are getting closer together? Because they're spiraling in. It's like that star that's going to merge. These are 2 black holes trying to merge. Now, they don't detect them out here until these things are going at least 30 times a second. There's a sensitivity limit on the detectors. So then they'll pick this up, and by fitting this with the models, they can work backward and tell you what's involved. The higher the frequency means lower mass. Higher frequency means they're moving faster. And think about inertia. It means you have less mass, you can make them go faster. That's one way. The duration of this also tells you things about the mass that's involved. So you can fit the whole thing together. All right. We now have another one online. This is the one in Italy. Virgo. On August 14th of this year, detection number 4, and all 3 detectors got it. Virgo was still doing engineering, and we probably would discount it if it weren't for the other 2 in the US that said the same thing. The waves came to each of these at a slightly different time. You know how they're arranged on Earth. It comes in and hits them different time. You can figure out a distance, a position, a location to look. Fortunately, not very accurately, but you can do something. So this is what you come up with. If you just had LIGO, it'd be somewhere, this is celestial sphere, there's the Milky Way. It would be somewhere in this band here. But when you combine the 3 of them, now we can put it down into here. Well, I'd love to run out with a telescope and look at that, except it's not nearly enough precision for the optical telescope. You've narrowed it down and say, I want you to find my house. And the first instructions I give you is I live in North America. Just drive around, you'll find it. Well, now we nailed it down to somewhere in the eastern half of the United States. Drive around, you'll find it. No, we cannot identify the location yet. But maybe we'll get this a little better. We're going to have more of these detectors, I hope, or too long. One of the big discoveries, though, we're getting so far was about black holes themselves, that we always thought that they only could be up to 20 solar masses as maximum. That's what we see in binary stars from the X-ray studies of the binary black hole systems. And so they only go up to about 20. These are all much higher. These are 30, 40, 50 solar masses. We weren't even sure you could make binary stars with that much mass. Obviously you can. I don't know if you understand that graphic. I had to look at it for a while myself. What they have across here is vertical is masses. Many of these are just spread out. And what they're showing you is this one and this one merged to make this one. So you can read the masses off, and they became this. This is the one they're not so sure about, so they got dashed lines on it. Here's another one down here, here, here. So there's 4 right there for sure, possibly a 5th. Apparently this is going on all the time. All the time. And you know the Nobel Prize went to these 3 guys. Yeah. Kip Thorne, the one on the right, did the theoretical calculations and promoted the building of this system. He has complained publicly that unfortunately they only gave the prize to 3 people. There's 1,000 people involved in the project. There's a limit by the way the Nobel Prize is set up. There's a maximum 3. And so these are the 3 that got it. We've got Rainier Weiss, who kind of conceived of the design on the left. In the middle, we got Barry Barish. He's credited of reviving this project when it died a couple of times. It was a shotgun wedding forced by the NSF between Caltech and MIT, and he kept those teams from killing each other as these things went forward. And Kip Thorne, who's the brilliant man who did all the calculations that are fitting the data, and he's the one that inspired the work. Well, that's a good place to stop, and when I get to a place like a conclusion, I always remember the words of that wise philosopher, Stephen Wright. We all should be tired right now. Thank you, gang.
Time for a question, but now with all that applause, we might have time for a question or two. Anybody have a question they would like to ask Ron? And he will be around for the rest of the conference, or at least for supper tonight. Any questions? One in the back. This is me running.
I just want to say I'm a Vera Rubin fan too, and that's a darn shame she didn't get a Nobel.
Yeah, I agree, yeah.
How about around for here?
I didn't know her, but I felt personally hurt when I got the news. Because, gosh, underappreciated and great observer. And you learn more about her story and and being a mother and all the details involved with getting a degree late and then fighting. Well, I kind of know people involved there. I got to be careful what I say. A bunch of stupid people, let's put it that way. Tend to be male. Anything else? I mean, want me to rant on something? I don't know. As Gary says, I will be around. You can ask me questions anytime. I'll have some kind of answer. Maybe it's sensible.
Supper.
Go eat.
Thank you, Ron.